Welcome to 2.3 Real Zeros of Polynomial Functions. This ultimately, a lot of this chapter, including 2.2, which was a big important section, could just be called the search for zeros. That's about 70–80% of what we're doing here. Okay, we've got a division algorithm here which seems really kind of mysterious. They go through, you can read through this, but they end up with this: a function equals another function times another function plus another function, just to describe f of x as three different functions here. And I'm just going to take this back to the time when you were doing some long division here, where you might take 5 goes into 42, and you would say 5 does not go into 4, but it goes into 40 8 times. And we know now we would write that as 8 2/5, or perhaps 8.4, but the first time you started doing long division, you would have perhaps said 42 divided by 5 ends up equaling 8 with a remainder of 2. Okay, so we're going to take those pieces. I'm going to try to make some sense out of this. We took 42. That was our dividend. That was what we were dividing. And we ended up getting our divisor, the thing we divided into it, 5. And I could take that times my quotient, 8, and I could add on to that our remainder. And that's all that's saying, and we'll spend a tiny bit of time with that, but it's not something to get too hung up on. Okay, the synthetic division, again, feel free to read through this. There's a lot going on with it. I think when you see it in action, pretty simple process, a little bit mysterious on how it works, but we will cover that in class, why this actually does some of the cool things that it does for us. But you'll be seeing some synthetic division. Branch off of the synthetic division, we have a remainder theorem, which says if we go through the synthetic division process, the remainder we end up with, which would be this very last value when we go through all of this process here, and you'll see it in action, becomes what f of k is. I don't have my glasses on, and I got small print here. Okay, becomes what f of x is. So what we end up with here, so if I want to find f of 7, I can just run 7 through this entire process, and what I end up with here is what f of 7 is. In the age of calculators, there's a lot of things going on in here that we relied on heavily many years ago, but in the age of graphing calculators, some of this stuff has become a little bit obsolete, but you're still going to be exposed to it. Okay, factor theorem. A polynomial f of x has a factor of x minus k, and this one is important for us, if and only if f of k equals 0. So in other words, if we end up with a 0 when we go through this whole process, then that k value is a 0. Like I said, when I put in 7, it turns into 0. 7 is a 0. 7 is an intercept. X minus 7 is a factor, and you'll see that in action. So this kind of reiterates what I was just talking about there. As you can see, there's a lot going on in 2.3. In summary, the remainder r obtained by synthetic division tells us the following things. If the remainder gives the value, or the remainder r does give the value of f when x equals k. So if I want to find an ordered pair that's located at x equals 6, I can just run 6 through synthetically, and whatever I end up with in this bottom position, that's what f of 6 is. So if I end up with 12, the ordered pair 6, 12 is on the graph. If r is 0, then k is a 0 if we synthetically divide through k, and therefore x minus k is a factor. And we talked about that back in 2.2. Okay, the rational zero test. This one's a little bit mysterious. I'm going to break through some of that mystery with you right here. Let's say we had a polynomial that was, let's say, 6x to the 5th plus 5x to the 4th minus 2x to the 3rd plus 4x squared plus 6x minus, let's say, 2. Okay, if we're looking for rational factors of that, we'd love to go through a big, long, drawn-out factoring process and get linear factors. A linear factor would look like this, ax plus b. So let's assume for a moment I can get a linear factor by going through some manual process out of this. That ax plus b, a would have to be, because I know, let's say we've got all these, let's say we're able to get 5 linear factors. I know that this times this times this times this times this would have to end up being 6. So a has to be a factor of 6. And likewise, b, this times this times this times this times this would have to be 2 or negative 2. So b has to be a factor of 2. So any factor we get, any linear factor we get would end up being a factor of 6 times x plus a factor of 2. And if I set that equal to 0 and solve for x, I'd get x equals, I would subtract a factor of 2 and divide by a factor of 6. So there's my rational number. A rational number is integers in a fraction form. And a factor of 2 over a factor of 6 could include all the factors of 2. Now, the negative really doesn't make a difference in here because my factors of 2 include negatives. So here are my factors of 2. They are plus or minus 1, plus or minus 2. Here are my factors of 6, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So I need to find all of my possible factors of 2 over factors of 6. And my factors of 2 on factors of 6 would include plus or minus 1 on plus or minus 1. That's plus or minus 1. They would include plus or minus 1 on 2, plus or minus 1 on plus or minus 2. They would include plus or minus 1 on 3. They would include plus or minus 1 on 6. And I don't need to put the plus or minus with the 6 because they all cancel and we just end up with those two possibilities, positive, negative 1/6. I would also have plus or minus 2 on 1, so plus or minus 2. We would also have plus or minus 2 on 2, but that's plus or minus 1. I've already included it. We would also have plus or minus 2 on 3, which I haven't included yet. And we would also have plus or minus 2 on plus or minus 6, but that's plus or minus 1/3. So here's the deal. Back in the old days, before your graphing calculator would sort out a lot of this for you, we would go through the process and find these 2, 4, 6, 8, 10, 12 possible rational zeros. And then we would start dividing those through our big polynomial and see if any of them actually work. See, this is no guarantee that even one of them works. So we might, and you might try 1/6 first and it works, and I might try 1/6 last and it's the only one that works. There were some points of frustration then, and you're going to see I'm going to free this up for you to use your graphing calculators to find some of the rational zeros along the way. But that's the rational zero test, and that's really what's explained here. Okay, Descartes' rule of sign and upper bound, lower bound rules. These, I have separate videos on our website that talk about that and kind of demystify what they're about. You'll see those when we get to those. That'll be on part 2 of this video. This is a very long section. Okay, so let's start putting some of this to work here. Long division first. Use long division to divide and use the result to factor the dividend completely. So just like I took 42 divided by 5 and set that up as 5 goes into 8, I'm going to set this up as 2x minus 3 goes into 2x cubed minus 3x squared minus 50x plus 75. And they're pretty much tipping us off that this is going to work out evenly. So I need to know, I ignore the 3 for right now. I need to know 2x times what's going to give me 2x cubed. I need to multiply this by x squared. So here's my x squared column. And I get 2x times x squared, 2x cubed, minus 3 times x squared, 3x squared. Now, what do I do with that? Well, I took 5 into 42 8 times, and I got 40. I subtract those. So right here, I subtract these, and this is a pretty big deal. It's pretty easy to make a mistake on this. The next thing I'm going to do is turn these into subtractions. So this would become minus, and this would become plus. Hopefully you can distinguish that with the red. I'm just trying to emphasize that. And here's the 0 I expected, and this is kind of a bonus 0 here. So what do we do next? Well, what do we do next? We subtracted and we brought things down. Well, nothing to bring down, but I do bring down this minus 50x, and I ask myself, what can 2x be multiplied by in order to get minus 50x? Well, it can be multiplied by minus 25, and that's just a regular old whole number. You might even put 0 x's here, because I don't need to multiply 2x by x. I need to multiply 2x by negative 25. And I get negative 50x, and I get negative 25 times negative 3 plus 75. I'm going to bring down this other plus 75, and I'm going to subtract those. Subtract opposites, opposites. And I end up with 0. So what does that tell me? That tells me that 2x minus 3 is a factor. In other words, this equals 2x minus 3 times x squared minus 25. If we FOILed this out, we would get this. It would be a good opportunity for you if you were on a quiz or a test, or really being careful on a homework problem. Be a good idea just to FOIL that out and make certain we get back to home base with that if we multiply those. Okay, so we did show that it was a factor, and now we're going, or use long division to divide, use the result to factor. Now we're going to factor completely. Well, factoring completely, 2x minus 3, x plus 5, and x minus 5, difference of perfect squares. How's that helpful to us? If I was going to sketch a graph, I would know I have a 0 at 5. I would know I have a 0 at negative 5. And I would know I have a 0 at 1.5. They're all single zeros, so they're just pass on through as if you were a line. End model behavior of this is a positive cubic. Wants to rise to the right, fall to the left. So this must look something like this. How high, how low does it go? Not really sure. One thing I'd be sure of on this, though, is that this would be all the way up at 75, because that's where this would start out at. So just another tool at our disposal if we're trying to figure out what a graph of a polynomial looks like. As I said, I'm going to open this up for Graphing Calculator quite a bit, but we're going to be able to go through these at this time for this section. Okay, number 18. Use long division to divide. So I'm going to divide this. Here we have to be careful. I'm dividing by this. I'm going to write it as x squared minus 2x plus 3. However, notice I've got an x to the fourth and no x cubes, and an x squared and no x's and a 1. I'm going to account for that. I have an x to the fourth plus no x cubes plus 3x squareds plus no x's plus 1. And if this 2x hadn't been here, this minus 2x hadn't been here, I would put a 0x right over here. So we fill in those holes that we have. Now, don't have to do anything other than long divide this, but there's no guarantee that this thing's going to work out. So let's take a look. X squared, I have to get to x to the fourth. I'm multiplying by x squared. So I go to my x squared column. I'm multiplying this whole trinomial by x squared. And I get x to the fourth minus 2x cubed. See how those line up well? Plus 3x squared. And what do I do next? hopefully you're all shouting. You grab the red pen and we subtract. I'm subtracting this, I'm subtracting this, I'm subtracting that. So I get 0. Really easy to make a mistake here. I get 2x cubed here. I get 3x squared minus 3x squared plus 0x squared, and I bring down the plus 0x. And I ask myself, x squared times what gives me 2x cubed? I need a 2, I need an x. So in my x column, I'm going to put a plus 2x so I can match this. 2x cubed minus 4x squared plus 6x. And what am I going to do with that? I'm going to grab the red pen and I'm going to subtract. I'm going to emphasize that every time you see me do a problem like this, I'm going to emphasize that subtraction. I think you can figure out why I would do that when I've been teaching this course for years and years. That's a really common mistake. So I get 0. I get negative 0 plus 4. I get 4x squared. I get 0 minus 6x minus 6x, and I bring down the 1. And I ask, what do I have to multiply x squared by to get 4x squared? Plus 4. So I get a 4x squared. I get a minus 8x. I get a plus 12. And what am I going to do next? Make certain that I subtract those. I get 0. Negative 6 plus 8, I get 2x. 1 minus 12, I get minus 11. So how do we represent our answer? Our answer, the division, is this guy, x squared plus 2x plus 4. This is our remainder. So let me take you back. What do we normally do with our remainder in a problem like this? We wouldn't write this as 8 with a remainder of 2. We would say that 42 divided by 5 equals 8, and we'd take that remainder and put it over there. And that's like having 8 plus 2/5. Doesn't mean 8 times 2/5. 8 and 2/5. 8 plus 2/5. So I'm going to just add on that fraction that we have remaining, 2x minus 11, which still would have to be divided by this. Just like that 2 still really needs to be divided by the 5 here. So 2x minus 11 still needs to be divided by x squared minus 2x plus 3. Okay. As I often say in this course, that's a problem where an example is just a whole lot of easy. There's just a ton of little places to make mistakes on a problem like that. Okay, synthetic division. I believe most of you have seen synthetic division, although I am certain that some of you who are taking one of the 2 courses has not seen synthetic division. So what we do is we set this up like this. I'm going to go 2, and I'm looking for holes. There's a 2x cubed, 14x squared, no hole there, so 14. I've got a negative 20x and a 7. If there were no x term here, I'd put a 0 here. That's crucial. Now, we will only synthetic divide when we have 1x plus or minus something. And what we synthetically divide through here is the MyVox. Negative 6 is what I'm going to synthetically divide through here. And here's how this works. First time viewing for some of you, review for most of you. I just bring the 2 down. I multiply these 2 together, negative 12, and represent it right here. I add these, 14 plus negative 12, 2. I multiply these, negative 12. I add these, negative 32. I multiply these, positive 180 and 12, positive 192, for a 199 remainder. Here's what this means. I divide it out in x. So this becomes x squared, this becomes x, and this becomes a constant. So the solution is 2x squared, excuse me. This was our cube, becomes squared. This was squared, becomes single x, plus 2x. This was an x term, becomes a constant, minus 32, and I still have that 199 that has to be divided by this x plus 6. Now, I don't know about you, but I think that's a lot slicker than what we had to do there, although it wasn't an option up on this. I hope that screen isn't showing right now. Sorry, I got a little blockage here with my computer screen. I don't think you can see it, but it's a little irritating to me. So Cortana trying to help me out here. I will be right back with you. Okay. Sorry. So anyway, pretty good process. Again, we have to have a plain old x, no coefficient in front of it. Can't do it with exponents. All right. In 37 through 42, we're to write the function as this product. So this goes back to this kind of strangeness that we had clear back here. So I'm going to synthetically divide. So this means basically I'm dividing this by x plus 2/3 when they tell me I'm dividing by negative 2/3. So we're dividing by k. So this is x minus k. I'm dividing by k is negative 2/3. So actually, truthfully, if k is negative 2/3, this is what I divided by, x minus k. So I'm dividing negative 2/3 synthetically into, and I think I'll have enough room for this, I've got a 15, got to be careful here, I've got a 10x cubed, I've got a minus 6x squared, I have no x's, 0 before I get to the 14. Have to do that. Okay, I think this is going to work out nicely. I haven't done this problem for quite a while, but if I remember right, they're giving us fractions. Sounds terrible, but might not be too bad. 15. When I multiply negative 2/3 by 15, I know I get a negative. I get 3 and 15 reduced to 5, and I just get 10. Well, that is nice. Add those 0, multiply 0, add those negative 6. Negative times negative positive, 2 times 6, 12, divided by 3, 4. Add those, I get 4. And one bad step here, multiply these, I get negative 8/3. Or multiply those, I'm sorry, negative 8/3. Okay, what do we have here? I've got 52/3 minus 8/3, is that 52? No, 42, excuse me, times 3. 42/3 minus 8/3, 42 minus 8, we get 34/3. And that's our remainder. So we can say that f of x equals what we divided by x plus 2/3. What we got out of that, I got 15x, this was to the 4th, so now it's to the 3rd. This was a 6x squared minus 6x squared underneath it. This would be a minus 6x plus 4, and then plus our remainder. And our remainder is 34/3. Just a little weird and quirky. Won't be a big portion of test. Might see a little problem on a quiz with that. Okay, 34. This is back to use synthetic division to divide. So here, this is the same as if it just said divided by x minus 3/2. If it just said this divided by that. So I'm synthetically dividing 3/2 into, careful, 3 cubes, 4 squares, no single x's, and a 5. So just a little fractional issue here. I get 3, I get, multiply these, 9/2. That's negative 8/2 plus 9/2. Negative 8 plus 9, positive 1/2. I multiply those, I get 3/4. Add those, 3/4. 0 and 3/4, 3/4. Multiply those, and I get 9/8. So my solution is, when I divide that, I get 3x squared plus 1/2 x plus 3/4 plus 9/8 on, what am I really dividing by? X minus 3/2. And I'm just going to clean up that compound fraction a little bit. Top and bottom, if I multiply the top and bottom by 8, I'll clean up this 9/8. I'll clean up that fraction here. So I end up with 3x squared plus 1/2 x plus 3/4, and let's see, I get plus 8's cancel, 9 on 8 times x minus 8 divided by 2, 4 times 3, 12. A little messy. Okay, so sorry I jumped around. I should have gone 26 to 32. Back onto this problem. This looks like it's going to be particularly nasty. I'm now synthetically dividing by -√5. Let's see how that works out. I'm taking that into 1x cubed, 2x squared, a minus 5x, and a minus 4. Let's see. Ooh, I'm going to wish I gave myself more room here. I'm going to write smaller than I'm already writing. So I get 1. I get -√5 when I multiply that. And when I add these, I get 2 minus √5. Hopefully something good happens here. When I multiply this times this, I get, I'm going to actually make this bigger. I'm going to reset this up. I think I'm going to run out of room here. -√5, poor planning. I got to give myself a little bit more room in here. You'll see why. Into 1, 2, -5, -4. Okay, so I get a 1, I get a -√5. I get 2 minus √5. When I multiply this by -√5, I get -2√5, and negative times negative positive, √5 times √5 plus 5. There's a little mercy right there. When I add these together, I just get -2√5. The 5's cancel. Multiply by negative, negative times negative positive, √5 times √5, 5, 5 times 2, 10, and I end up with 6. So how do we write our solution? Our solution is, it would just be, I'm not going to put f of x there because it was f of x we were dividing. Our solution is, this is an x squared plus 2 minus √5, which needs to be multiplied by x, minus a plain old 2√5. That is being multiplied by x plus √5. And we had a remainder to add on to that, which was plus 6. There's our remainder. So again, that's equivalent to what we did earlier when I took 42 divided by 5, got 8, remainder 2. We said 42, what we started out with, could be equal to what we ended up with, 8, what we divided by 5, plus the remainder 2. What we ended up with, what we divided by, plus the remainder. And these two, of course, could be changed. Okay, I'm going to call it a, we're at the 29-minute mark now, so I'm going to call a break on this one. I will show your assignment if you want to, if you're getting started on that, but this will definitely be in another part, maybe another 2 parts. So this is the assignment. Obviously, that would, what you've seen so far would allow you to get through 39, because I have examples up through 40. Okay. Come back, check the second part, but that should get you started.